When humans read a Python script, we read it like a document. We scan from top to bottom, looking for a narrative or a logical recipe to understand what the code is supposed to do. But the machine does not read for meaning. Developers write scripts that seem logical on the screen, only to watch them fail upon execution. The logic makes sense to the human, but violates the invisible rules of the execution environment. The Python interpreter operates as a rigid mechanical engine. It advances through code by following absolute laws of mathematical state and binary logic. To write code that executes as intended, you have to manage 4 distinct mechanical domains: isolating memory scopes, evaluating strict branching logic, driving iterative engines, and traversing sequences. You have to stop viewing code through a human lens and start anticipating the machine's exact mechanical steps. We start with memory. When a variable is referenced, the interpreter performs scope resolution. It searches a strict hierarchy to find the data, checking the local scope first, then the global scope, and finally the built-in namespace. Whenever a function executes, it spawns a temporary local frame. This acts as an isolated sandbox for data, existing entirely within the broader global environment. The local frame can read the global variable. However, if you attempt to assign a new value to that global variable from inside the function without a specific instruction, you trigger the global modification trap. Python creates a new local variable with the exact same name, leaving the global state unchanged. To override this defense mechanism, you must invoke the global keyword. This provides an explicit instruction to the interpreter, granting the local function permission to modify the global namespace directly. Python isolates memory by default. This architecture ensures that temporary functional tasks cannot accidentally corrupt the program's permanent global state. This block of code defines a void function. It executes a sequence of instructions, but it generates no reusable data for the rest of the system. The print statement inside it is a terminal side effect. It displays text on a screen for the human operator and then immediately discards that data from the interpreter's working memory. If the interpreter reaches the end of a function's execution block without encountering a specific return instruction, it implicitly returns the void keyword none. To create a fruitful function, you must use the return statement. This is the official bridge mechanism. It passes the computed data back out to the calling expression right before the temporary local frame is destroyed. While the print command serves the human monitor, the return statement is absolutely required for the machine's ongoing mathematical operations. Once memory is managed, the interpreter has to make decisions. Multi-branch statements, using if, elif, and else, are processed as mutually exclusive logic gates. These gates follow a rule of absolute exclusivity. The moment one Boolean expression evaluates to true, its block runs. The machine then skips all remaining elif and else branches. To build complex conditions, developers use compound logical operators, and, or, and not. When evaluating these compounds, Python uses short-circuit evaluation. The interpreter will stop evaluating an expression the moment the final outcome is guaranteed.
For the AND operator, both sides must be true. If the machine checks the first operand and finds it as false, the entire statement cannot succeed. The interpreter aborts immediately, leaving the second operand completely unchecked. The OR operator works in reverse. Only one side needs to be true. If the first operand evaluates to true, the statement is already guaranteed to succeed, and the second operand is similarly skipped. Control flow is a process of optimization. The interpreter searches for the fastest possible way to abandon unnecessary computation. When a sequence of code needs to be repeated, Python relies on 2 distinct iteration engines, the for loop and the while loop. A for loop is a finite operation. It iterates over a known container, like a list of numbers, automatically advancing its internal loop variable until the container is empty. A while loop is a condition-based engine. It has no fixed endpoint. It runs continuously as long as its core Boolean expression evaluates to true. Operating a while loop requires 3 mechanical steps: initialize the variable, check the condition, and execute the update. If the update step is omitted or mathematically flawed, the Boolean expression will never evaluate to false. This causes the machine to become trapped in an infinite loop. To track data continuously across these iterative cycles, developers use the accumulator pattern, a dedicated variable designed to save running totals. The state variable for the accumulator must be initialized outside and above the loop. If placed inside the loop body, it will be overwritten and reset to 0 on every single pass. Without rigorous state management and a guaranteed update mechanism, iterative code can fail, resulting in a system-halting infinite loop. Iteration becomes more complex when handling multidimensional data, like a 2D matrix storing grocery product names and their corresponding prices. Single-loop logic cannot address a grid. To process it, the machine must use nested iteration, a secondary loop spinning entirely inside the primary loop. This requires synchronized mechanics. The outer loop pointer locks on to a single row index, holding that state still while the inner loop pointer scans the columns. The inner loop must complete its entire cycle before the outer loop takes a step forward. Only when the column scan finishes does the outer loop move to the next row, triggering the inner loop to restart from 0. Processing multidimensional matrices requires you to track 2 different scales of state execution simultaneously. Tracing these specific mechanics in unison provides a clearer view of the machine's execution path. The interpreter plunges into a nested loop, locking row indices and scanning columns, bypassing code the moment a short-circuited logic gate evaluates to false. A function is called, spawning a temporary local namespace, pulling in arguments and initializing an accumulator variable outside the repetition engine. The iteration completes. The final value crosses the boundary via the return statement, arriving in the global namespace as the temporary local frame is destroyed. Adopting the interpreter's perspective, focusing on isolated memory frames, Boolean gates, and accumulator states, provides a technical foundation for predicting how the machine will process your code.